physics. Today we are going to be learning physics. What is physics? Physics is a pure science. Physics is a pure science that deals with the behavior of matter and energy. That deals with the behavior of what? Matter and energy. And their relationship with other physical properties. Is that clear? Yes. So physics is a pure what? Science. Pure what? Science that deals with the behavior of matter and energy and how it relates with other physical properties. Physics is a pure science that deals with the behavior of what? Matter and energy and how it relates with other physical properties. So physics is a pure science that deals with the behavior of matter and energy and how it relates to other physical properties. Or you can say how they relate to other physical properties of the matter, isn't it? There are some things that happen in the world and you say physics helps explain. So what are the examples of physics in nature? Right. Examples of physics that we witness every day. Right. Number one is what? Driving. The process of driving a car can be explained using what? Physics. Number two, lightning. The lightning that comes around before thunder. You understand? The lightning that comes around before thunder can be explained using what? Physics. Number three, the working of a thermometer. The working of a thermometer. How the thermometer works. You understand? At high temperature, you see the fluid in the thermometer moving up. So those movements, the motion can be explained using what? Physics. What other thing? Camera. Camera. The working of a camera. The working of a camera. So you can see that in our line of learning in physics, we'll be able to explain all these things. All these things fall in one aspect of physics or the other. So physics is a pure science that deals with the behavior of matter and how it relates to the other physical properties. And things like this that will happen in an everyday living, like driving, lightning, thermometer, and camera, could all be explained using what? Physics. Using what? Physics. Now we are going to look at measurement. Measurement is a very important aspect of physics because physics works with quantities. Physics works with what? Quantities. So all these quantities, you need to know their size. If you want to explain their behavior, you need to know their size, isn't it? If you say that something is very hot, how hot can that thing be? A boiling water that is very hot, can you use it to make tea? But you can use the one that is mildly hot, isn't it? You can easily drink that one. So how do you know that the one that is mildly hot is not as hot as the one that is boiling? How do you know? Through what? Through what? You need to measure so that you know that this one is hotter than this one. That's how you can explain the properties of things or quantities. You need to measure to know the difference. Water that is cold and the one that is ice dumped, two of them are not the same temperature, isn't it? So how do you know? How do you measure? If you're measuring temperature, you use thermometer, isn't it? So you can measure every other thing. So what do you measure? You measure quantities. What do you measure? You measure what?
Quantities.
Quantities. Measure quantities. So this quantity can be length, it can be weight, it can be time, it can be any other thing. Is that clear? Is that clear?
Yes.
So we have two major quantities. Two major quantities. Physical quantities are measured to ascertain their size. Physical quantities are what? Measured to ascertain their size. You need to measure them. And there are two types of quantities. In physics, we have two types of quantity. In physics, we have how many types of quantity? Two types. We have number one called the what? Fundamental physical quantities. You understand? Fundamental physical quantities. Then number two, we have the what? Derived physical quantities. So these are the two types of quantities we have in physics. Fundamental physical quantities and what? Derived physical quantities. Fundamental physical quantities and derived physical quantities. So these fundamental physical quantities are basic what? Quantities. With what? Basic units. So they are basic quantities with basic units. So the three major examples of fundamental quantities are length, mass, and what? Time. The three major fundamental quantities are what? Length, mass, and what? Time. Length, mass, and what? Time. So length is represented as L, isn't it?
Yes.
And it is measured in what? Seconds. Is it?
Yes, sir.
Mass is represented as what? M, and it's measured in what? Measured in what? Kg, kilogram. Time is represented as T, and it's measured in seconds. Seconds. This one is the length is actually measured in what? Meters. M. Isn't it? So these are the three main fundamental quantities. Length is measure of distance from position A to what? B. This distance. That's length. Mass is a measure of the total quantity of matter in a substance, isn't it? Whereas time is the measure of what? Duration. Time is the measure of what? Duration. So the three fundamental quantities in physics are length, mass, and what? Time. Length, mass, and what? Time. But there are other fundamental quantities. What are the other fundamental quantities that we have? Apart from length, mass, and time. Oh. There are other fundamental quantities. Take your notes.
Electric current.
Good. Electric current. Electric current is also fundamental quantity. Another one is what? Luminous density. Luminous density. Luminous density is another fundamental quantity. Another one is what?
Amount of substance.
Amount of substance. Amount of substance. Amount of substance, which is mole.
Yes.
So it's another fundamental quantity. What other fundamental quantity?
Thermodynamic.
Thermodynamics temperature. Thermodynamic temperature is another word, physical, fundamental physical quantity. So you can say that the fundamental physical quantities are what? Length,
Yes.
mass, current, isn't it?
Yes.
Temperature, luminous density, amount of substance, mole. You understand? Those are the fundamental quantities. They are not gotten from other quantities. Unlike the derived quantity. So we have two types of quantities in physics: fundamental quantities and what? Derived quantities. So what are derived quantities? These are quantities obtained by combining two or more fundamental quantities by multiplication or division. Is that clear? So what are derived quantities? Derived quantities are actually gotten from fundamental quantities. You understand? Derived quantities are quantities obtained by combining two or more fundamental quantities by multiplication or what? Division. Derived quantities are those quantities that are obtained by combining two or more fundamental quantities by multiplication or what? Division. So we're going to go into details of what derived quantities are. We're going to go into details of what derived quantities are. So we say derived quantity. Is it? What's the next column? Definition of the derived quantity. What's the next column? Basic interpretation. So who can give me an example of derived quantity? Velocity. Velocity. What is the definition of velocity? Is what? Displacement over what? Time. So you see, velocity is derived from two fundamental quantities of displacement and time. This displacement is certain at distance, isn't it?
Yeah.
And it's represented with what? L. Time is the same thing as time and it's represented with what? T. So you can see that these two fundamental quantities, L over T, combined using what? Division, makes a what? Derived quantity. Can you see? So derived quantities are got from fundamental quantities that are combined by either division or what? Multiplication. Another example of derived quantity is area. And area simply means distance times distance, isn't it?
Yeah.
Or length times what? Width. Length times width, that is area, isn't it? Yeah. And length here is distance, L. Width is also distance, what? L. Which is the same thing as L what? Square. So this is a derived quantity, isn't it?
Yes.
So give me another example of derived quantity from there.
Acceleration.
Acceleration. Acceleration is another example of derived acceleration. I hope I got the spelling. Acceleration. Is it correct? Yeah. Acceleration.
Easy.
Yeah.
Yes.
You understand?
Yes.
So what is acceleration? Acceleration is what?
Velocity over time.
Increase in velocity over time. Or you can say velocity, change in velocity over time. You understand? And velocity, as we know, is already L over what? L over T. Isn't it? So divided by another word, T. Isn't it? So this will give us what? L all over T squared. Is that clear?
Yes.
So you see, this is a combination of basic quantities giving us a what? Fundamental quantity acceleration. What other example of derived quantity do we have?
Walk. Walk.
Walk. I want us to go gradually from line to force. Force is another derived quantity. So what is force? What is the definition of force?
Mass times acceleration.
Mass times what?
Acceleration.
Acceleration. Is it?
Yeah.
Good. So if we are interpreting in terms of dimensions, we have mass M times acceleration is what? L over what?
T.
T what?
Square.
Is it not? This is acceleration. So making this to be what? M L over what? T squared. So this is derived quantity. Acceleration. What other derived quantity do we have? Work. So what's the definition of work?
Force times distance.
Force times what? Distance. You can see that one derived quantity is almost following from the other one, isn't it?
Yes.
Using their combinations. So what is force? We already know that force is M L over what?
T
T squared. Already. So times what? Distance, which is what? L. Giving us what? M L squared all over T squared. Isn't it?
Yes.
Which other derived quantity do we have? Energy, which is the same thing as work. That's
Speed.
which other one? Speed. Speed is similar to velocity, isn't it?
Yes.
If we have speed here, what would be the definition of speed? Speed is what? Distance over time, which is also the same thing as L over what? T. It's just that the difference between velocity and speed is that while velocity is a what? Vector quantity, speed is a what? Scalar quantity. So velocity is displacement, which is movement in a specific direction. You understand? So this one has direction, whereas this one does not have direction. So vector quantities are those quantities that have both magnitude and what? Direction. Whereas scalar quantities are those quantities that have magnitude but no clear.
Yes.
Is that clear?
Yes.
Good. So we'll stop this and we'll go further things later. Yes, welcome back. Today we are going to be learning dimensions in physics. Today we are going to be learning what? Dimensions in physics. Dimensions in physics. And what is dimension, or what are dimensions? Dimension of a physical quantity indicates the way the fundamental quantities of length, mass and time are represented using the letters L, M and T. Is that clear? So what is dimensions? We can simply say that dimension of a physical quantity indicates the way the fundamental quantities of length, is it? Those are the fundamental quantities of physics from the last lectures we had. We have length, what? Mass, and what? Time. And what?
Represented by the letters.
Are represented by the letters L, M, and T respectively. Is that clear? Is that clear? So dimension is simply dimension of any physical quantity indicates the way quantities of length, mass and times are represented by the letters L, M, T respectively. You understand? Whenever you have any derived quantity, derived quantity is always made up of some fundamental quantity, isn't it? So the way they are arranged, using the letters LMT indicates the word dimension. Is that clear? Is that clear? So it can be used to indicate the fundamental quantities of a physical quantity. So use it to indicate the fundamental quantities. Example is when we talk about speed. What is speed? Speed is what? Distance over what? Time. So how do we represent the dimensions of speed? We know that distance is the same thing as length, isn't it? Length. Because distance from A to what? B is the length from A to B, isn't it?
Yes.
So distance here is L. Time is what? T. So we can say that speed is the same thing as L, T, right, isn't it?
Yes.
Because all over division sign you can change it with this, isn't it?
Yes.
So this is the speed is equal to LT to power minus 1. So this is the dimension of what? Speed. Because we say that dimension is simply what? The way the physical or fundamental quantities are what? Indicated or represented. So the fundamental quantities here are what? L and what? T. Is that clear?
Yes.
Is that clear?
Yes.
Another example is what? Acceleration. Another example is what? Acceleration. I would say that acceleration is equal to what? Velocity over what? Time. Isn't it?
Yes.
What is velocity? Velocity is what? L over T. Isn't it?
Yes.
Time is also what? Also divided by T. So this L over T is what? Velocity. All over T. Is it? So we can have what? L over what? No, this is actually L over T, which is velocity, divided by what? Time, which is the same thing as L over T times 1 over T. Isn't it? This is velocity over time. Velocity is already L over T, divided by the same thing as over time. Isn't it? Then this is still equal to the same thing. But here, if you want to change the division sign to multiplication, you have to, instead of writing T, you have 1 over what? T. So if you break this down, you have L all over what? T squared. Is it? And L over T squared is the same thing as saying L T to power minus what? 2. So this is the dimension of what? Acceleration. That is the dimension of what? Acceleration. LT to power minus 2. Is it?
Yes.
Is that clear? Acceleration is equal to velocity over what? Time. Which is equal to velocity is what? L over T. Is that not the dimension of velocity? Yes. L over T divided by what? Time. This time. Which is the same thing as saying L over T times 1 over what? T. Which is the same thing as saying L all over T squared. Which is the same thing as saying L T to power minus 2. This is the dimension of what? Acceleration. Is that clear?
Yes.
Is that clear?
Yes.
Now we're going to do more difficult aspects of this dimension. But before that, we are going to learn about the application of what? Dimension. How do we use dimension? Application of what? Dimension. Application of dimension. Number one is we can use it to find the true relationship between what? Between physical quantities where the what? Where the correct what? Mathematical what? Relation or formula cannot be easily obtained. So this one way we use dimension. When there is a statement in physics and we don't actually know how to write the formula, you understand? We can use the knowledge of dimension to break down the statement into mathematical relations. You understand? Which is, we are going to do some examples. So one of the major applications of dimension is to find the true relationship between physical quantities where the correct mathematical relation or formula cannot be easily obtained. So if you cannot use mathematics to find the formula, you can actually use the knowledge of dimension to break it down. Is that clear? Number 2 application is that it helps to find the true unit. Is it? The true unit of a physical quantity. Dimension can help you in determining the units of any physical quantity. Is that clear? It helps in determining the appropriate units of a physical quantity. You can say true or what? Appropriate. You understand? You can use the knowledge of dimension to find the appropriate unit of any physical quantity. Is that clear? So which is among what we are going to be learning very soon. So we are going to look at an example. We are going to look at an example of how to apply this dimension. So let's look at this example. Examples in dimension. Number 1. Let's look at this. In an experiment. Right along. In an experiment, a string fixed at 2 ends is plucked. It would be seen to vibrate. The velocity v of the wave produced depends on the 1. I. Tension F in the spring. 2. Length L of the vibrating spring. And number 3 is mass M. This implies of the wave produced is proportional to tension. Length of the string and is